Oh, good morning, everyone. So, to begin with here, I have the exam scores in. I'll be writing a grade book out for everyone where the homework and worksheets are at and where everyone's standing. I just perused them. I haven't transferred everything into the main grade book. Working on that now. Started last night for one of my other classes and finished my four sections of 162. Now I'll do your section and then my 143s. That said, if anyone had any problems, just email me. All right, keep in communication. Let me know what's going on. I will send out my weekly blast of where we're at, what we need to do, and go from there. We have homework on graphing due a week Sunday, and homework due this Sunday from the previous stuff that we were doing, solving algebraic equations. Work on the homework. If you get any questions around the homework, always ask. I'll try to put some videos up, or I'll talk about them in here. All in all, good job on the exams from the scores I'm seeing. So, thank you for that. And I'm gonna get started. We're gonna talk about lines. Yes. Well, so I'm gonna look at them. Janine asked, did we get our exam scores right after we took it? It would show you a score, and you had the ability to retake it if you didn't like the score. Um, and that score is, from all intents and purposes, what's going in the grade book. I'm double checking to make sure there's not like one question everyone gets wrong, because I can see what the answers were entered in. If I need to, I can do partial credit. This one does not look as bad as my 162 one. There are a couple things where people flipped their signs and got no credit, and I had to go through and kind of give partial credit for that. So in this one, the score that Pearson is showing definitely looks like it's what's going to be in the grade book, but I won't say for sure. I do want to review everything yet. I don't let the computer tell me exactly what to do all the time. And there's enough stuff in there that I can look to see if any partial credit is justified. That being said, what you don't have in the grade book is the worksheet grades, what quiz grades we've had, the quiz slash worksheets, and the homework you have on Pearson, but none of it has been weighted. And what I normally do is I put that on the front of the exam. So for the first exam, you would get your exam grade, and then by the second exam, you would have your exam grade and the average exam grade, and your homework grade and your quiz grades, and then where your class grade would be at that point. It would kind of come in little packets on the front, and I would do that for there's three exams, so you would get that three times during the class period. Because I'm not physically handing things back to you, I'm doing that in email. So I'm at the process of putting that back. If this would have been in class experience, and let's say the exam was just done, I'd be handing it back Monday. Is where this conversation is going. There's some processing going on. That being said, see, I wish I could animate those lips so it could look like me talking. Or, well, not me. That's not really what I look like. I could make the talking face. All right. That's what I have on the exams. Remember, you can always go back through and redo the homework. If you have any problems or need anything, email me. And I will be doing my bi-weekly email of the status of things tonight. On that note, I want to talk about lines. We're talking about linear equations, and we have a good setup. So just kind of a recap of what we've been talking about. So we have invented or at least historically someone has invented for us, this thing called a Cartesian plane. So I kick way off to the side here. I did not mean to. There we go. Get back to my origin. We have this Cartesian plane, which we have labeled the axis. Oops. The x-axis. I'll put a hat on it to let me know it's an axis. And the y-axis. And any point could be a set of two values in there. And so at any point, I'll just arbitrarily say, I'm going to build what I want to do bit by bit here as I do my recap. So we'll say we have a point 1. So point 1. It's over a certain distance in x. So I'll go 1, 2, 3 in x, and 1, 2, 3, 4 in y. So there's point 1. It's 3 in x, 4 in y. And we list our points in alphabetical order. The x and then the y. And so I want 3 over in x and 4 over in y. Now, because space is divided by these axes into 4 distinct areas, we have quadrant 1, which I'll write in Roman numerals, quadrant 2, quadrant 3, and quadrant 4. In those areas of space, numbers have similar properties. Everything in quadrant 1 is positive. All the x and y values are positive. Everything in quadrant 2 has a positive y and a negative x. Everything in quadrant 3 is negative. A negative x and a negative y. Backwards in x, downwards in y. And everything in quadrant 4 has a positive x and a negative y. And so that's why these quadrants are distinctly labeled. If we see something in one of those quadrants, we have an idea of what its value is without even needing to know the exact value. That's what putting these things in space let us do. They also let us start describing equations and relationships by how it appears to us visually. And so one of the things we learned is if we have 2 points, they can define a line. So let's put point 2 here. So if point 2 is at 7, 0. So that's point 2. You gotta remember, I'm recapping what we've been talking about. So if I'm going quick, this is why I'm going quick. I'm talking about all the things we talked about before and putting it all into one place. It's because we're really going to focus on lines specifically. And so I want to make sure that I'm just setting the stage, so to speak. Now notice, I'll say something about this point. It's 7 over an x and 0 in y. If you have a 0 for one of the coordinates, if y is 0, you're on the x-axis. If x is 0, you're on the y-axis. Which actually becomes a useful thing to help us solve for. Setting things equal to 0 is something we do because it makes doing the math a little bit easier, and it will tell us when we cross the x or y axis. So that fact that if y is 0, you're on the x-axis becomes very useful for us. And we'll see that, I think, a little bit better when we start seeing the equations. But any 2 lines, or any 2 points, whoops, I don't want to use that color. Any 2 points come together in a line. So, try to draw my line as close off to infinity as I can. And so the existence of those 2 points defines a line. I can connect them with a line, and anywhere on that line, I can talk about another set of xy values. And so we'll say, hey, there's a third point down here. It's x comma y, but I don't know what it is yet. But this line contains an infinite amount of points. So there must be some rule that we can use to find what those points are. And so the rule is what we're slowly building. Well, what can we say about this line before we pull exact numbers out of it? Because there's one other thing we discussed that is going to define lines for us, and that's this thing has a slope. Right? It's going downward. I can borrow what I know from geometry, what I know from having to go up and down stairs, from having to walk on hills. Right? In general, we talk about things going from 0 and getting bigger. So our x values get bigger. Well, as our x values get bigger, the y values get smaller. And so we say this is decreasing because as x gets bigger, y gets smaller. So there's a preferred direction that we talk about things. And it's the same direction we read in, going left to right. And so this line has a slope that's decreasing. And we write slope as the change in the y value over the change in the x value. Or we subtract two y values from each other over two x values from each other. And since this slope is decreasing, it's going to have a negative value. Negative slopes decrease, positive slopes increase. And the number of the value tells me how steep the line is. So if I have a line that's -6, it's decreasing really quickly. Right? A -6 slope, let me draw a -6. I'll do it from the same point here, roughly, -6. Would be like this, right? We could say, hey, that's a m equals -6. It's a steep decrease. While a small fractional line, we'll say m, oops, that was not a line. That was a squiggle. Right, we'll do a shallower line. Well, that m is equal, looks like that one looks like a -1/8-ish, right? So the larger the number, the steeper the line, the smaller the number, the shallower the line. If it's negative, it's decreasing, and if it's positive, I'll draw a positive line out here. Sorry, I'm trying to draw all these lines from one point so we can compare them. That's roughly an m equals 1. I was trying to draw an m equal 1. So positive lines increase, negative lines decrease. The larger the number, the steeper that increase or decrease is. And so we have set up 2 points here, point 1 and point 2. So I'm going to calculate the slope of these. And I'm going to do this in red again. I know it's getting busy here, but I want to visually compare these things. And we kind of broke this down before. And what my goal is here is to do this new thing, which is how do we describe any point along this line? And what we're going to do is we're going to make a linear equation. But first, let me find the slope. So y2 is 0, right? Because there's y2. Minus y1, which is 4. There's y1. Over x2, which is 7, minus x1, which is 3. And I get -4 over 4, or -1. This is a slope of -1. So what we've been able to do with this idea of slope is we can attach a number to an idea, and that number changes when the thing in reality changes. And that's how fast or how quickly these lines go up or down. And we're gonna, how fast or quickly they go up or down, we're gonna say is their rate of change. Sorry, we've got plants in the porch. The porch is like a sunroom, and I'm pretty sure this is where my allergies are going to start kicking in. So you'll hear me sniffly coffee in the porch, allergy wise, probably on and off for the semester as I learn to fight the pollen and dirt infested, not infested, infused teaching area that I'm now in. All right, so we were able to do this now where we can attach a number to how lines move through space. I can say this thing has a rate of change of -1. Now it's the rate of change in y related to x. What's nice is that this concept we can attach to anything that has a rate of change. It doesn't need to be going up or down in space. It can be distance versus time. We'll turn the slope into speed, which is the last example we showed last time. But what I want to focus on right now is that, hey, I have a value for things, but I need to figure out every point on this line. Some way that I can talk about this x3 value for this point will tell me what its y3 value is. There's some way that I can figure out, since this line does everything for me. It goes through space. It keeps this relationship related to its rate of change. And we're going to learn some equations to do that. And we're going to learn some examples to do that for linear equations. I could go through and tell you exactly what this line is right now, but what I want to do is we're going to come back to it because we need to build the things. And we need to build the things up. And I want to make sure that we build up into each part of this rather nicely for us. So what I'm going to do is I'm going to look at the 3 ways that we can write an equation for a line, and then we'll come back to this. So I'm going to scroll down a bit here. And I'm going to write 3 forms of a linear equation. Oh, and I'm trying really hard to find colors that pop on this. I have tried this white with black to make it look like a whiteboard. I do not like that. I definitely prefer a blackboard look for it. I'm trying to get colors that look like chalk. Occasionally, some of these things don't shine through as bright. If there's anything you want to, like, you're like, can you please stop using that fluorescent pink? It's not, or neon pink. It's not the 80s anymore, Jeff. You need to get over it. And I'll laugh and giggle. But I also switch colors when I switch ideas. So if it does look like a rainbow threw up on the screen sometimes, just say, hey, start a new screen, right? You got your little thing off to the side here that you can shout out at. Do we determine which coordinate is which in terms of x2 or x1 with the direction of the line? Janine's asking, and now I'm going to scroll back up because I was slow to see the little thing on the side here, but there is a small delay on it. Determine which coordinate is x2 and x1. So what I did here, when I did my y2 and my x2, is I picked point 2 for that. I'm going to, in yellow, reverse this. I'm going to say, hey, I'm going to go the other way. I'm going to say this is point 1 and this is point 2. So if this was point 1 and this was point 2, I need y2, 4, right, minus y1, 0, over x2 minus x1. So I flip them. They're in a different order. Well, I get 4 over -4, which is also -1. So what I want to show you there, Janine, is that it doesn't matter the order you do the points in. I can subtract this point from this point, or I can subtract this point from this point. But what is extremely important is if I call this point 1, then in this is x1 and y1. They have to come together as their pair. So notice 3 and 4 are over each other here, and 7 and 0 are over each other here. And when I do it over here, 4 and 3 are over each other, and 7 and 0 are over each other. So you can do these in any order. You will get the same numerical answer, which is nice. That actually shows this thing has good value. Doesn't matter which point we start on, the line we walk is the same. But what is extremely important is the two numbers that define a point always come together. So if I'm calling this point 1, like I did here, then that's x1 and that is y1. If I'm calling this point 2, like I did over here, then this is x2 and this is y2, right? These always have to have the same label. Janine asked a good question and I got really excited. Sorry if I was shouting on that, but that is, it's one of those nice things math does. It makes sense sometimes, right? Once we peel through the onion and get to see what it's doing, it's consistent. And a lot of times we're like, okay, y2 is always the second thing, y1 is always the first thing. And when we're going to map the real world into our mathematics, and we have that choice to choose the first thing or the second thing, we sometimes lose the fact that the order actually didn't matter. It was a great thing to have the steps, but there's a lot of choice in how we start mapping things through. All right, so there's 3 ways we can write an equation for a line. The first one is going to be general form. And it says ax plus by equals c. And a, b, and c are real numbers. Now, later on, if you take Math 126 or Math 162, depending on which math classes you need for your major, you will sometimes see that A, B, and C need to be integers, no fractions. Oops. Need to be integers. And A has to be greater than 0. A has to be positive. You'll sometimes see some books do that restriction on this. I'm okay right now with A, B, and C being any number because that's how your book is going to do it. You'll find that the general form does get used in higher mathematics a little bit more than I'm going to use it because we can't see any information out of general form. In fact, there is a standard form. I'm going to slow down, get my handwriting a little better. Which is the general form with everything set equal to 0. These two are identical. There's a technique called matrices and vectors that this is very useful for. We will touch upon this a little bit, just a wee bit. All right, we'll get used to this form. But the form we're going to use is called the slope-intercept form. where m is the slope of the line, and b is the y value when x equals 0. The reason we like this form, or are going to like this form, or I'm going to try to get you to like this form, is because these numbers on the end tell us information that we can see right out of our so these numbers pop right out. So let me just show you what I mean by these m and b on the graph that we did before. Oops. Yeah. My scroll keeps dropping down to the bottom. Something up with my mouse. Oh, I know why. It's because my pen was on the tablet. There we go. Sorry about that. All right, let me get back there. There we go. So this line, this orange line that we were talking about, and why I focused on this point here, which I'll draw a really big dot on, that's y equals b. It's the intercept, the y-intercept. It's where the line intercepts the y-axis. And so if I know this number and I know the slope of the line, I can describe every point on the line. And so seeing the -1 and seeing the b in the equation, I can go, oh, it's here, and it goes down or up at a certain rate. And so those two numbers are going to give us kind of visual clues that we can drop onto our graph. And that's what we're going to be working on today. But let's look at what I mean by these forms, because we're going to want to see some equations in different forms. So why is it saying insert chart over there? I hate when this, there we go, sorry. 5x plus 3y equals 10, where a equals 5, b equals 3, and c equals 10. So this is general form, and we're looking at what the values of a, b, and c are. Notice x and y, we don't give a value. We're using these variables truly as variables. They can take any number. And so I could have a combination where x was 2 and y was 0. Because if I plug 2 into here, I get, well, let me plug it in. Well, 5 times 2 is 10, and 3 times 0 is 0. It's 10. So this point, 2, 0, is on this line. This equation describes an infinite amount of points, and they're linear. And so by being linear, any pair of points could come on here. Let's see. There's a lot of weird fractions in this particular one. I could have x be 3 and y be, let's see, 3, no. If x is 3, that's 15. I want that to be, let's see, without mapping it out fully. Well, here, let's use our technology to show us this. I set this up earlier and I should use it. There we go. So I'll come over here to my graphing utility. And here's the line. 5x plus 3y equals 10. So I typed in my equation of my line over here on Desmos. It plotted my line through space. So all of these points, here I have, what do I have here? I have 5 comma negative 5 is a point on this, because what, see, 5 times 5 is 25, and negative times 5 times 3 is negative 15. 25 and negative 15 is 10. Here is 2 comma 0, the point I showed you. Here is 0 and 3 and 1/3, right? But all of these points satisfy the equation of the line. And so you see how I'm scrolling through here and I get a different number pair. All of these answers, all of these points right here, 3.62 and negative 2.7, well, they're acceptable values for x and y that satisfy the equation. So when we say an equation of a line has an infinite amount of points, it has all of these answers that for possible x, y. Just not the ones we can see, but every possible one. So that's why, no pun intended, these stay as variables. The x and y stay as variables. We let them vary. We let them vary the value so that they can talk about any one of those pairs. And so what was one of them? We could have 5 comma negative 3. That was a possible pair too. So looking for the easy numbers, but there were a lot of fractions in that one. And so this general form of a line talks its way through all of the possible values. The thing I want you to really focus on is, for now, x and y do not get numbers. They're open containers. They are truly variable to represent any possible number that works in the equation. I'm going to go back to this graph again to highlight that. This equation here, 5x plus 3y equals 10, shows all possible points for x and y. Each one of these things highlighted, or as I zoom around on this, represent every value x or y could take. And so x or y does not have one set of values. It doesn't even have something we solve towards. It's every possible value. There are infinite values of x and y, and they all lie on the line. This rule, putting this rule together, restricts the values here. In fact, I could create another line. I'm going to create 6x minus 2y equals 12. So 6x minus 2y equals 12. And I now have all of the points for this line. They're completely different points except for one where they cross. But they're still infinite. They're an infinite pair of values that satisfy this rule. And it's a different rule. And so the reason we write them in the same form is so that we can observe this rule here, 5x plus 3y equals 10, is a different rule than 6x minus 2y equals 12. Well, why is it a different rule? Because those numbers in front of the variables, the a, b, and c in the general form, are different. Only when the numbers end up being the same do you get the same line. And so these forms help us see what our lines are going to be. But our job, our main job, is going to be translating into these things, these 5x plus 3y equals 10, and a 6x minus 2y equals 12, into something that has a slope. And so that's going to be a large portion of our work ahead for us. All right. So that's the general form. All right. Now I want to get back to what we can do with our lines here. let's go to this. And we're going to look at something we have done before in a new form. So I'm going to have a general form of a line. And I don't have the technology. I don't have anything I can to get values from it. But I want to have an idea of what this line is doing. So we made tables before when we needed one value. Well, we can make a table of X and Y values. Now, your book does these horizontally. It does them here. It does them like this. It does X, Y, and it'll put like a 0, a 1, a 0, a 1, and then you fill in the other one here. Every place I've ever done it before, I do them vertically, where I do my X value and my Y value like this. Again, it's just a way of doing information. Again, I'm probably going to do it slightly different from the book, which is why I'm pointing it out. I don't want you to go, why is he doing these up and down? And the book does them left and right. I think a lot of that has to do with the way I was taught mathematics was first line down. And so I do a lot of things in columns. I'll work my way from the top down in solving a problem, not left right. And so information tends to go into columns. And for me, this lets me, any work I need to do with the equation can go down here, and any work I need to do with the table can go here. I kind of divide things into columns. If I do it horizontally like the book does, it kind of cuts across the page. So just letting you know, if you go look in the book on the table values and you see them doing left and right, no difference. All right, so let's look at what we can do with this. Well, I always said 0 and 1 were good values to find. So what I need to do is I'll start with X. What happens if I put in 0 for X? So 4 times 0 plus Y equals -5. And I want to find my Y value. Well, that gives me 0 plus Y equals -5. Or Y equals -5. So I have my Y value there. All right, well, I'll continue. I'll put in a 1 for X. So 4 times 1 plus Y equals -5. 4 plus Y equals -5. I'll subtract 4 from both sides. So that equals -9. And we repeat this for other values. But I can also do the same thing over here. I can say, hey, you know what? What happens when I put 1 and 0 for Y? What would be my values for X? I don't have to keep moving just my X values. In fact, what I want to do is I want to make the math as easy as possible, right? So 0 and 1, they're a little bit easier to calculate, usually, right? We still make it fractions. So I'm going to do these in red. So I'm going to put in 1 for Y. So 4x plus 1 equals -5. I'm going to subtract 4 from both sides. So 4x equals -6. Divide by 4, -6 over 4, or -3/2. So that's -3/2. So I'm trying to fit this all on one screen. I apologize for that. And now I'm going to put in 0 for Y. And so 4x equals -5. I'll divide both sides by 4. So I get x equals -5/4. And I have the beginning of my table. So choosing good x and y values doesn't always lead to nice, easy non-fractions. It happens. You're going to see because that we have this slope hanging out in the front, because there is a fractional rate of change possible hanging out behind these things, behind this thing, because the slope defines the relationship, and the slope is based off of a fractional concept. Fractions come back. Sorry, I can't stop that. Right? It's there. Okay. Let's move through. Alright, well, we have these in general form. We've done our graphs of them. And now we want to find slope. So, one of the best ways to find slope is to look at our two forms. All right, I wanted to save this because I wanted to come back to our original equation. So give me a second here. I'm going to save as part 1 of today. All right, that's saved there. And I'm going to open a new one of these. There's that. I have a new blackboard. I'm trying to do this without crashing out memory, because this opens up a pixel and a pixel. So this image is 88 megs in size. And I just add or subtract the pixel values from it as it goes through. Makes it work really smoothly, but I just don't want to crash out memory with the stream running here. Oh, Janine. Yes, that is correct. Sorry, I didn't see your question there. Though it is off the lecture subject, so I'll just type that in there. All right, so we want to look at how we can move from ax plus by equals c. We want to move in form to y equals mx plus b, because this form is going to tell us things. And so we want to move from one form to the other. One form to the other. Well, notice y is all here on its own. So what we do, neighbor kids across the street running around, which is okay, they need to, is we solve for y, leaving x as a variable. That's the technique we do to move from general form to our slope-intercept form. From general form to our slope-intercept form. From our general form to our slope-intercept form. And you can do the opposite to go back. But let's first do this version of it. So, 2x plus y equals 3. Yes, Janine. It was across the street. My neighbors have a fenced-in garden, and their children play there. And they're two small boys and their dog, and they're playing a tag or something. And you know how, well, kids being kids. I've got 4 boys. I went through this phase too, where the sheer excited joy of playing comes out in whoops and wallops. Let them have their joy. Let them have their joy. All right, so 2x plus y equals 3. So my job is to solve for y. So I want to get y on its own with a positive 1 in front of it. So to do that, I'll subtract 2x from each side. But here's the thing. I want to do this in a way, these will cancel, that hangs out in front. And so this was a positive 3. So it's going to look like this. Notice I don't know what x is. X could be a negative number. This all becomes positive, right? And so we have this instinct where we would like to write this equivalently like 3 minus 2x, right? So we like our subtractions looking like this. But our form that we want is y equals mx plus b. So we need something out front. So here I went from general form. I isolated y by subtracting the 2x. So y was on its own. But when I subtracted that 2x, I made sure it stayed out front. Because, and I'm going to try to highlight this in a bright, obnoxious color like white. There's my slope. It's hanging out in front of the x. I can say my slope is negative 2. And my y-intercept is 3. By having this form, I have the ability to actually sketch this graph. I could sketch this graph. I'll do it really small down here. And then I'll do it in software so we can see why this form is nice. And you'll get practice going back and forth. So my y-intercept is 3. So I go up 3. 1, 2, 3. My slope is negative 2. So I go down 2, 1, 2, over 1. Down 2, 1, 2, over 1. And so my line looks like that. This form lets us see those two pieces of information. Where this crosses the y-axis. It crosses the y-axis at positive 3. That's what the b is telling me. And then my slope tells me, well, I go down 2 over 1 because slope is rise over run. And so I can have negative 2 over 1 or 2 over negative 1. So that says down 2 over 1, up 2, back 1, up 2, back 1, up 2, back 1. So this form shows us what we need for the line. Let me put this on my graphing tool. And I want to put it both ways. 2x plus y equals 3. Over here. So the one thing I want to notice here is I put the 2x plus y version of this in red. Right there. When x is 0, y is 3. That's what that intercept means. I go down 2 over 1, down 2 over 1, down 2 over 1. That's what my slope meant. Well, let's put it in our slope form. We had y equals negative 2x plus 3. And look, they're the exact same lines. The blue lies over top of the red. And so we get the two different forms give the same line. These are equivalent equations, but what's nice about this second form is I see my slope hanging out in front of the x, and I see my y-intercept as the constant on the end. And my y-intercept is that big dot right there, 0, 3. It's where I cross the y-axis. I cross the y-axis at 3. But right there is that 3. That 3 is there, and I'm getting this information. That's why we like this form. It doesn't do anything mathematically better, but I see two numbers that I can use to put this on the graph. The slope tells me how it's moving. Because it was a negative 2, I knew it was going down, and it was going fairly steeply. And if we look at this line, it's going down and fairly steeply. The plus 3 at the end tells me where it's starting from. It's starting from a y value of 3. And so having the equation in that form, I get, there's my starting point, and I'm going down fairly steeply. And that's what we're going to learn to see in these things is going down steeply, starting at 3. Y equals mx plus b. Going down steeply, starting at 3. Y equals mx plus b. Yes, I do broken record things, but math is a lot of weird rules about patterns. Something about visualizing math has always helped me take some of those rules and attach words to them, or what they look like they're doing, instead of memorizing a whole bunch of rules. And I have found that very useful for me mathematically. I am not a rule memorizer. I tell you that over and over again. There are certain ones that I've done so many times that I've memorized them by doing them over and over again. There was a time in trig where the way the one teacher taught was to prove all this stuff. It took the Greeks years and years and years, and the proofs are really, really large. Just memorize them, because trig was a very useful thing before calculators came about. And so it was still taught that way, that you had to memorize all these rules for trigonometry. And it almost killed me mathematically in high school doing trig. When I went back later in college and was learning trig and pre-calc, I learned enough of the ways to put them together that they fell into place. I am not a memorizer, but if I can visualize something or I can see what it's doing, this pattern I can put in my head. And for me, and I highly emphasize this form isn't any magic. We're not really talking about what y equals, right? Well, we can, and this will help us when we do word problems. But what we're really doing, or I'm hoping we're really doing, is we're putting it into a form so when we look at it, it reads information to us. And the y equals part is a good setup for saying, this is my slope, which tells me how fast it's rising or decreasing, increasing or decreasing, and where I start. And so when I see this and there's no powers to x, it's a sentence for me. Here's my rate of change, here's my starting point. Rate of change, starting point. All right, now that I beat you over the head with the same mantra over and over again, let's look at a couple others here. All right, there are 2 intercepts. There's an x-intercept and a y-intercept. I talk a lot about the y-intercept. Let me talk enough about the x-intercept so you'll see some questions about it in the book. An intercept is where you cross an axis. And a line is going to cross each axis once. Because it doesn't curve, it doesn't bend. So, I have these right. Yep. This point is 3, 0, and this point is 0, 4. So this is called the x-intercept because it crosses the x-axis. And this is called the y-intercept because it crosses the y-axis. I look at the axis and note that to get to the x-axis, that's where y equals 0. And to get to the y-axis, that's where x equals 0. There's a little bit of a reversal going there, right? I am on the y-axis when x equals 0. That y-x flipping. I am on the x-axis when y equals 0. That I don't like to say it. I like to draw it. Because when I draw it, I can look here and go, hey, these are my x values. These are my y values. If that's my origin, then my y is 0. If I go to say it as a sentence, I will flip my x and y's around all the time. You've noticed that with signs and things. I have this little bit of a dyslexic tendency on these. So I always go back to my graph on this for what it is. Intercepts are really important because if I have the form y equals mx plus b, if I put in 0 for x, I get y equals b. And that's the definition of the y-intercept. If I put in 0 for x equals 0. But if I put in 0 for y, I get this thing here. 0 for y equals mx plus b. And that's y equals 0. And that tells me where my x-intercept is. We're going to find that when I take a line and I need to solve it for one value, we can usually rewrite it into this form, because notice I only have one variable now. And this, throughout all of algebra, pre-calc, and calc, becomes what we call our solutions, or roots. All right, so there's some previewing of where things come, right? But what's important for us right now is my x or y, I can set them equal to 0. If I set x equal to 0, if I set x equal to 0, there's no x value, I am stuck somewhere here on the y-axis if x equals 0. And so when x equals 0, I am crossing the y-axis. I am intercepting the y-axis. If I set y equal to 0, why is it equal to 0? Why not? No. And if I speak in England, they'll call 0 naught. And so this would be y naught. Okay, it's an English pun for English people. I'll behave. So I'm working with the. Did I not? Thank you, Tina. It should switch over in a second, and I'll go back and point that out. Now, if I were savvy here, right, I'd go up on YouTube and I would edit the clip over. I've got to get the chat to ding in my headphones. It's not. Wait, maybe I have a thing to do that. That's interesting. No. There you go, Tina. Sorry. That was a whole bunch of verbalness that I was trying to explain. What I want to do is I want to get a drawing utility on top of the graph so they go together. All right. Whoa. I'll re-explain all of this. So this is our form. Y equals mx plus b. And I had to throw in that really bad pun in there too. What I'm trying to get set up here. And I will take a break. We've talked a little bit here, and I've got to re-explain this, so I'll clear a mental break here. Is everything's on one computer screen for me right now, so I switch between windows. And when I flip the what I'm displaying, to see the chat, I have to move some windows over. And so if I lose the chat bar, or I'll sometimes lose the window I flip to. And it's just, I've made this mistake a couple times here and I realize it. What I want to do is get a second monitor so I can see nothing but the YouTube feeds. I can see your chats and respond to them. And at the same time, also be able to see kind of what I'm doing. Because I can only see the application I have. But so for a bit of a reprieve, I'm going to go to moving camera mode. So, and I know I've showed you this before. I've got a standing desk with my sound equipment. I've got a microphone to the side of it. And then over here, I'm waiting for my camera. Yeah, there's storage in the back. And the other microphone. I can't chew gum and walk. I've tried. I trip. Or I bite my tongue. And then I actually have a blackboard that the camera is going to go on so I can get back to chalk at some point. And what I want to do is somewhere off to where the window is into the house here. It's back into my house where my lava lamp is going. And here's me all disheveled. All right, I'll turn this back to blackboard. And what I want to do is get a big monitor up there so I can see your chats, because the way I have my screen right now, I have two windows up. The smaller one is the thing that switches between the different screens or the screen I'm working on. And so you'll hear me click on the mouse as I have to go to the thing that switches the screen. The bigger window behind that is the YouTube feed. And what I've done is the chat bar comes down the right hand side. I've made all my windows small enough that I can always see the chat bar under that. But occasionally, as I'm juggling things, especially when I go to the web browser and have to switch on a tab that isn't the YouTube tab, I'll do what I just did there. So that's my explanation for that silliness. Me apologies. And I'm going to re-explain this. So I have a lot of things drawn here, but I'll work back through. We have this idea of 2 points, 3, 0, and 0, 4. Because this point is where we cross the x-axis, it's called the x-intercept. And because this point is where we cross the y-axis, it's called the y-intercept. But notice, if I'm anywhere on the x-axis, my y equals 0. So the x-intercept is where y equals 0. If I'm anywhere on the y-axis, I hope you can see the dot moving up and down here, x equals 0. And so b, a y-intercept, is where x equals 0. Well, what I can do is I can take my equation, y equals mx plus b, and I can set x equal to 0. And when I do that, this term goes away, because anything times 0 is 0, and I get y equals b. I'll write over that, y equals b. But that's the definition of the y-intercept. This b part is the y value when x equals 0. So it falls back out of our equation. In fact, when I said I had a hard time memorizing these things, I wouldn't even call it the y-intercept. I would just say, what happens if I set x equal to 0? I get b. What happens if I set x equal to 0? I get b. Because this whole term here goes away when I make it equal to 0. Because anything times 0 is 0, that leaves me b. But that ends up being how we define the y-intercept, because when x equals to 0, I am somewhere around here. I am stuck on this y-axis. And so that b value tells me where my line crosses it. Well, the same thing happens here. If I set y equal to 0, I get 0 equals mx plus b. And I can solve for x. And so when y equals 0, I'm stuck somewhere along the x-axis, the x-intercept. X-intercepts are the useful part of algebra and functional algebra, all the way up until you do multivariate calculus. So x-intercepts are useful things. They're also probably the more difficult concept, because when I solve equations for setting y equal to 0, I shift the equations or the functions I'm working on. While the y-intercept, I think, is functionally a little bit easier to see because it's part of the form that we see. And so you're going to see a lot of focus for me here on y-intercepts. What do they mean? Y-intercepts, what do they mean? But we will plug in 0 for y to find x-intercepts, right? And as we start solving problems, we're going to start seeing or building the patterns that talk about this. But this is more of a 126, 162 thing when we start going, x-intercepts are roots and solutions, especially when we have weird functions. These are our intercepts. Let's look at solving some intercepts. Let's see if I can do this and keep the right screens going. I am really sorry about that. I hate when things go wrong. I hope I didn't overly stress everyone out. Tina, thank you for saying it up there. Sorry, I was standing like a foot away, pointing at the windows at one point, and shouting because I came up with a great pun. I'll have to save that pun for another class. Alright, so let's look at our intercepts and what we can do with them. Let's see here. Get my example problem on. Come down here. Good, I have new space. So 2x plus 3y equals 6 is what I'm going to be looking at. So 2x plus 3y equals 6. All right, so this equation I want to graph. And what the book is saying is, okay, don't put it in y equals mx plus b form yet. Find the x-intercepts and the y-intercepts. So we're going to do what the book asks of us here for right now. So the y-intercept is when x equals 0. So I'm going to come over here and I'm going to say, hey, I'm going to put 0 in for x and leave y as what it is. Well, anything times 0 is 0. So I have 3y equals 6, or y equals, I'll divide both sides by 3, I get 2. So the y-intercept is 2. The x-intercept is where y equals 0. So I'll come back over here and I'll do the same thing. I'll leave my 2x alone, but I'll put in 0 for y. And anything times 0 is 0. And so the x-intercept is 3. And what the book says is, you know what? You have enough information now. Oh, let me do this in neon green. Actually, I'm going to do this right down the middle of all the parts of this because I'm going to be as sloppy as I can be so you all hate me. No, I'm just going to save some space here. Here are my axes. So if my y-intercept is 2, let me come up 2, 1, 2. 1, 2, so that's 1, 2. So Janine asked the question, how do we know x is equal to 0? For a line, there has to be some point where x equals 0. So we're not saying we know it equals to 0. We're going to say, hey, there's some point where it equals to 0. What is the y value at that point? So we're not saying we know it equals to 0. We're saying we know there is a point where it equals to 0. What's the y value that goes with it? Trying to change the language a bit. And I think your second point, yes, that's what we plug in. We plug in 0 for x to see what the y value is. And I'll show you in a second when I'll go back to the graph to show you that any line has to cross the x or y axis somewhere. So there's 2, 1, 2, 3. There's 3. So there's my y-intercept at 2. That's y equals 2. And there's my x-intercept at x equals 3. And just having those things means I have enough information to draw the line. And if I have graph paper, I could find any value I wanted of the line using this representation of it. So if finding the x and y intercept is easy, it's not a bad way to go. Now I'm going to note one thing about this line. And I'm going to do it as a question. Ask yourself, what's the value of the slope of this equation? And don't think of the number, but think of the direction. This slope is going down. So m should equal 0. And so there's a couple different ways we could find the slope. So I could say, I'll take this point here as 0, 2, and this point here is 3, 0, because that's where they're at. And I could say y2 minus y1 over x2 minus x1, or negative 2/3. I have a negative 2/3 slope. Well, I can rewrite this equation now because I know the y-intercept. So I can say y equals, correct, Janine. Now you know how long my delay is. 2/3, I'll take that slope, x, plus my y-intercept, 2. And this is the same as this. That's a lot of work to do that. Couldn't we do it another way? Why, yes, Jeff, we can do it another way. 2x plus 3y equals 6. I'm saying that's equivalent to this. Because I found the intercepts and I found the slope, I put my slope and my y-intercept together in this form. Well, let's isolate y. So I'm going to subtract 2x from both sides. That leaves me with 3y over here. I'm going to write the negative 2x out in front. I'm going to divide everything by 3. So I divide everything by 3. Hey, look. They are the same. I like it when math does what it advertises it should do on its tin. Y plus 2, because there's 3 reasons it's plus 2. Let me come up here. So if I put in 0 for x, this term goes away, and I get 3y equals 6. So if I divide both sides by 3, I get 2. That's my y-intercept. So wherever I use the y-intercept, it's a positive 2. So when I come down here and I use it in the y equals mx plus b, it's a positive 2 also. All right, I'm ending on one thing here today, and that's going to bring me back to the first thing we looked at, where I said, hey, we have a slope here between these 2 points. I need to find the equation of the line. If I have intercepts, I can find the equation of the line fairly nicely. But what I'm going to do here is I'm not going to have an intercept. I'm going to have 2 points. Now, what I'm going to do is I'm going to use the equation of the slope, something we already defined between 2 points, and I'm going to do something with one of the points that will let us get more equations out of this. So this is a weird argument, but bear with me here. It's okay, I confuse myself all the time, right? As long as we ask the questions and unravel the confusion. Sometimes that leads to more confusion, but we get there in the end. Now I'm putting parentheses around the numerator and denominator because those are things that are hidden. But the numerator and the denominator are one thing. So that's my definition of slope. If I have 2 points, I can find the slope. But I want an equation of a line where I have a variable. Let's do variables in bright red. I have variable x and y. So, well, I've got 2 points. I said, and I'll hold by this, you need 2 points to make a line, or you need a slope and another point to make a line. So you always need 2 pieces of information. Well, I have the information for slope, and I have the information for 2 points. I have 3 pieces of information. I'm going to get rid of one of these. And so what I'm going to say is, hey, you know what? My x2 can hold any value. I'm going to let it vary. And my y2 can hold any value. I'm going to let it vary. So this is going to let me rewrite this equation. So I'm going to say my slope is equal to any y value minus my 1 point over any x value minus 1 point I know. All right. This is actually really, really useful. I know, lots of weird letters. Where's the usefulness for it? Bear with me here. I'm going to multiply both sides by x minus 1 x1. So I'm going to clear the fraction. So I'm going to multiply this side by x minus x1. And I'm going to multiply this side by x minus x1. Now the reason I did that was to clear the fraction. This will cancel over here. I'll scroll up a bit here. And I get x minus x1 equals y minus y1. I'm going to rewrite this. I'm going to, whoops, got my m in there, right? M. There's the m. So I'm going to rewrite this. I'm going to put the y minus y1 in front, and the m equals x minus x1 in the back. And this weird, ugly relationship is called the point-slope version of the line. And the 2 major forms of a line you're going to use are mx plus b as the slope intercept, and then in the point slope version. These are the same. This is a very specific point. This is the point 0 comma b. So if I put in 0 for x1, because this is the thing that's my actual point, this gives me mx. Oh, here, let me do that. Let me switch the 2 instead of saying it. So the way I use this is I have y minus y1 equals m over x minus x1. I have a slope and a point, x1 comma y1. If I plug my slope and my point in, I will get my equation for the line. Well, let's look at this, which says we have a slope and a y-intercept. And a y-intercept is a very specific point. So I'm going to plug in 0 for x1 and b for y1. Well, x minus 0 is x, so that becomes mx. And I'll add b to each side. Gets me back to here. So the point-slope version of a line is the slope-intercept form, except it doesn't really tell us the information visually. But what it's really useful for is solving the problem that we started with. So I'm going to take this version of the line, y minus y1 equals m x minus x1. Notice, I'm going to put boxes around those. Those are the things we put values into. I'm going to put big red underneath these. These are the things we leave alone so that we have an equation coming from them. And I think that's the hardest part when first doing this, is we're used to always finding a value for x and a value for y. And now there are things that we will find that we put the values in. We will find m and b. We will find m and x1 and y1. They'll get numbers. but y and x stay on their own so that we get equations. Right, and that's the slightly different thing. But as you go through the homework, you'll get some good practice with this. All right, so I'm going to take this form with the thing that we did originally. Let's see if I can open what we did originally here. So file, open recent, part 1. Yep, I did it really small though, but there we go. Let's come down here. Let's scroll this a little bit more in the middle. All right, so the points I initially looked at was 3, 4, and 7, 0. And I got this orange line here. And I said, hey, we're going to find the equation of the line. We know its slope. Went through all the effort to find its slope, but we didn't find the equation of the line. So I'm going to come back up here, and I'm going to take these 2 points, 3, 4, and 7, 0. So P1 is 3, 4, and P2 was 7, 0. Make sure I'm looking at the right thing. I want to go back. I said we're coming back to this. Okay, P1, 3, 4, P2, 7, 0. We found a slope of -1, and we want to find a y equals mx plus b form. In fact, we want to know what that dot is right there. All right, so let's use this new formula. Y minus y1 equals mx minus x1. I have 2 points. I need to find a slope. Now I'm going to repeat finding the slope. I know we already did this, but I'm going to repeat it. So I need a point. Well, I've got 2 of them, and a slope. So I'll start by finding the slope. I'll go back to red. So m equals delta, the change in y, over the change in x, which equals y2 minus y1 over x2 minus x1. So y2 is 0, minus y1 is 4, right? y2, y1. x2 is 7, and x1 is 3. So I get -4 over 4, or -1. So my slope is -1. My slope is -1. All right. And we knew that. We saw that on the graph. But we want an equation, and we want the y-intercept without having to graph or find these things. So I get to take any one of these points and plug it into here. Well, I've got a 0 hanging out here, and zeros usually make math easier. So I'm going to use this as my point. So I'll do that in green now. So I get y minus, well, what is the value of my point for y1? 0. What is my slope? -1. Right? Because I found my slope here. X is still a variable. Doesn't have any subscript, so it's a variable. Minus, well, I've got a 7 here. So I'll put the 7 there. So y minus 0 is y. And I'm going to distribute this -1 to each term. So I get -1 times x plus 8. Notice this is in the form I want now. I have my slope, and I have my y-intercept. So if I come down here, scroll, that point is y equals 8. But I now have an equation of the line. Well, Jeff, you said it didn't matter which point I used. But I don't believe you. So we're going to look at the other point also. I think I'll use neon pink to distinguish. So my points are 3, 4, and 7, 0. I'll use 7, 0. So I'm going to come back up here, and I'm going to use the other point. I'm going to use y minus y1, but I'm going to use this now for the bright purple. So y1 is 4 minus 4 equals, my slope is still negative 1 because we found the slope, that's good. X is still a variable, but now I have minus 3. I did something really, really, really silly. And you should catch me on it here. Negative 1 times 7 is not positive 8. It's positive 7. I added, I didn't multiply. Sorry about that. I'm really excited because I was near the answer. Let me get back to my bright purple part here. Because I'm getting excited again. So I'm going to keep the y minus 4 over here. I'm going to distribute this negative 1. So I get negative 1x. Why do I keep adding 1 to this today? Plus 3, right? Negative 1 times negative 3 is positive 3. I need more coffee! Right? Negative 1 times x is negative x. Negative 1 times negative 7 is positive 7. Negative 1 times x is negative x. Negative 1 times negative 3 is positive 3. Well, I'm going to add 4 to both sides here. And look, I get the same thing no matter which point I choose. As long as I multiply and don't weird add or whatever I did there. Sorry about that. I caught it. I caught it. And I left it on video on YouTube forever. Woohoo! No, it's okay. So what I want to do is I want to do a quick summary of the tools that we have here. We need 2 pieces of information to get an equation for a line. And those can be the slope and the intercept, the slope and 1 point, or just 2 points altogether. Any of those information, we can get the equation of the line. Slope-intercept form is y equals mx plus b. Point-slope form is y minus y1 equals mx minus x1. Where the ones are the values from the point, y and x you keep as variables. When you do this, this spits out a y equals mx plus b. Once you put all your numbers in, you're going to turn it into this. And the other tool we have is we find our slope. Like this. In fact, this tool here really makes these other tools happen. Sorry about my mathematical error. Sorry about the bad puns. No, sorry about the bad puns. Be safe. Be well. Until again, email me all the questions you have.